My name is Dan. Hello. I'm going to talk to you all about a problem that I encountered recently that has caused me a great amount of anxiety. So this gap between a program and its proof shall serve as the simulacrum for that anxiety through the duration of this talk. But before I get into the weeds of what I mean when I talk about this gap, I'd like to talk about a little bit about how I came to know about this problem. Now, I work on autonomous vehicles. What we're looking at here is a vehicle which we can assume has some level of autonomy given the plethora of sensor systems that are on it. We see cameras and radars and lidars in the front and in the back, but there's also a smattering of acronyms here. This ASIL A, B, C, D. Now, ASIL stands for Automotive Safety Integrity Level. And it kind of prescribes a spectrum of rigor that we should apply to some component in a vehicle architecture, which corresponds to how safety critical that is in the overall architecture. So you can imagine something like the window motor. If the window motor fails, it doesn't really go beyond just being kind of annoying, particularly on a very cold day. The failure of the window motor is not going to be catastrophic for the vehicle or for the persons in the vehicle. On the other hand, something like the power steering system or the braking system. Now, if there is a failure in that type of system, it's going to be catastrophic for the safety of the car and for the people in the car. So this is something that we apply the highest level of rigor to. And this is something that we would say was ASIL D rated, where the lowest amount of rigor is ASIL A. Now, when we're talking about the software architecture for an autonomous vehicle, it tends to look like this. Is kind of a reductive logical architecture for an autonomous vehicle where we have some set of sensors that are pulling data in from the outside world, and that's getting fed into some AI or ML that is doing computations, it's making inferences, and it's ultimately turning those inferences into some decisions. And those decisions are doled out to some other subsystems that are responsible for actuating in the vehicle. Now, I personally don't work on this AI box here, which is where you usually think, or what you usually think of when you're thinking about the tech in autonomous vehicles. It's where all of it is focused. I work on the infrastructure in the cars, which would be like these arrows that are coming into the AI, coming out of the AI, as well as these systems that are responsible for turning those decisions into commands for the subsystems of the vehicle, like the steering, the throttle, or the braking. And I kind of fundamentally believe that this infrastructure in the vehicle ought to be rated at an ASIL D level, and I can kind of give you an example of why. The data that is coming in from those sensors, before it is useful to the AI, it has to be translated. It has to be sort of in an information theoretical way into something that the AI can understand and perform computations on. And simultaneously, oftentimes this data from these sensors is also being fused together from all of the disparate sensors into some format that's easier for the AI to then perform computations on. We call this sensor fusion. And in this process of fusion and translation, we want to have the most possible certainty that we're not compromising the integrity or the fidelity of that data before it reaches the AI. Because if we did, it would cause the AI to fail to be able to make proper inferences. We've actually seen examples where a single pixel can cause a computer vision algorithm to cease to be able to recognize simple objects. Now, on the other side of the AI, coming out of the AI into these actuators, we want to have, with high certainty, that the messages are being received in the communication protocol, and also that when those commands are received by the systems that are responsible for actuation, that they do exactly that, nothing more and nothing less. And so when we have a component in a vehicle that is ASIL D rated, we are required to apply some formal methods to it, some kind of mathematical reasoning, or maybe it's model checking or something like that. And it is through this that I came to know this problem, this gap between a program and its proof. Now, there are some sort of traditional approaches to this problem, and we'll take a look at those first. The first option is just me. I, as an observer human being, I say this program and this proof, totally the same thing. I've written a program in one language, I've written a proof mathematically or in some proof assistant, and I give them both thumbs up, and you have to trust me. So you can imagine writing some grand, beautiful, and elegant proof, and it shows that all of the properties about the program that you care about hold, and it's wonderful. And then you write your program, and the extent of it is something like this. Obviously, this is a ridiculous and hyperbolic example, but the point that I'm trying to make here is that there's nothing mechanical that tethers the proof to its program. and vice versa. So another approach to this is to extract a proof, or extract a program from the proof assistant in which we've reasoned about that program. Now, the proof assistants that are popular in specifically my domain in automotive is mostly Coq, a little bit of Isabelle and higher order logic family, or AGDA, a little bit of AGDA. But the languages that we can extract from in those proof assistants tend to be these functional languages like Haskell, OCaml, or Scheme. Isabelle can do some ML and some Scala for some crazy reason. But unfortunately, none of those languages are an option for me in this architecture. And that is because, especially we're talking about the actuation down here, they're small systems that may have a real-time constraint, or perhaps it's just an embedded system. Maybe it runs on a microkernel that doesn't have a full POSIX environment. So a language that is lazily evaluated or has non-deterministic memory management is just not an option for me. So typically, when we are met with these constraints, we choose a language where we can manage the memory deterministically, where we're responsible for the memory management. We use something like C or C++. Now, if we could extract a C program from a proof, then that would be a solution to this problem. And there is actually active work to pull a C program from a Coq proof. And here is a small example of some code that has been extracted from a Coq proof. If we look at line about 106, you see that we're doing a math operation to index into a buffer, bitwise ORing, casting, and shifting left all in one line. Now, subjectively, this code is terrifying to me. I would never want this to be in some car that I expect to keep me safe in any way. But objectively, given the constraints that I have in these systems, I would have to teach the extractor for each individual sort of ad hoc platform that I have to deploy these systems onto. So I would be rethinking the extractor for each process, and it just becomes an untenable problem. And secondarily, the standards body that gives us the ASIL sort of ratings say that if you have code that is generated or extracted, don't look at it. It's fine. Whatever came out of some other tool, don't even review it. So you are wholly trusting in the extraction process. And in most cases, this extraction process isn't even verified by the proof assistant from which it is extracting a program. So we're once again left here with this problem where we have one system that is wholly observational and has no sort of mechanical way of tethering a proof to a program. We have another one that is totally mechanical and is very difficult to reason about as a programmer, because I am a programmer, I'm not a mathematician. I want to write a program and then be able to reason about that mathematically after the fact. So what if there was another option that we had, some way that we could kind of think about what it means to run a program and how we can make that overlap with a proof about that program? But before I get into those details, I'd like to take a slight digression about this sort of bifurcation that we're presented with when we are talking about formally reasoning about a program or a programming language. We are presented with this idea of syntax, and these are the syntactical objects that we're actually actively working with when we're writing our programs. This is the things like structs and 8-bit integers, and it also is how scope is managed, and things like curly braces and semicolons and all of this. And it describes our programs syntactically, but on the semantics side, we're more talking about what it means to run that program. What is its model? When we give it some output, when we give it some input, what is the output of that program? Now, there's several approaches to reason about a program semantically, and the one that we'll focus on for this talk is something that is called denotational semantics. And its raison d'etre is to glue the syntax of a program to some meaning in some other more universal language. Here is a couple of examples. We have some 8-bit integer, an unsigned integer, which we would think about through our sort of semantic function that maps it to some meaning as the set of the natural numbers such that they are all less than or equal to the number 255. We have the same example here for an unsigned integer of 16-bit width, and it has the same kind of rules applied to it. So the takeaway here is that we are mapping our syntactical objects to the universal language of mathematics. And so through this denotational semantics, we can start reasoning about our program in a mathematical way. So given that, I'd like to talk a little bit about type theory. Now, type theory is a foundational and constructive way of reasoning about mathematical objects. You typically see it written in this way. We have some term and some type. As a concrete example, you would read this as saying that true is of type bool. The thing on the left is called a term, it's the value, and the thing on the right is the type. Now, type theory is also computational. In the same way that a program is inherently computational, we are walking through a program and computing the commands line by line, type theory can also capture this notion of computation. What we're looking at here is called an inference rule for a type theory. And the way that we read it is we say if the statement above on the top of the line is true, then we can infer the statement on the bottom line. The characters that we see on the far left here, we have first a gamma and then a thing called the turnstile. The gamma is what is supposed to be our context. It's the things that we know thus far as we're doing these inferences, or it could also be the other rules that we have like this that tell us how to make inferences about other types. And then the turnstile denotes assertion. So if we were to read this rule out loud, we would say that given our context, we know that A, the term A has type A, and the term F is a function that maps A's to B's. And when we apply F to A, we can infer that we will get something of type B. So if we can model computation in type theory, can we capture the semantics of our program entirely through this framework? And it turns out that no, not quite. Type theory, a simple type theory in and of itself is not sufficient for actually reasoning entirely about our program. It's just not a rich enough system. So there is another option. This notion of dependent type theory is the idea that you have some type that is dependent on a value or a term from another type. So what we're looking at here is called a pi type. If we were to read it, it would say that for us to produce a B, I first need a value of type A. If we use our bool example before, we would say that to produce a B with true would be a completely disjoint type from producing a B with the term false. So this means that B is a family of types, but to actually produce one of those families, I first need to have a value of the type on which it depends. Now, in the same way that a type theory is computational, so is dependent type theory. We can apply this same application rule here, except for in this case, when we apply our F to our A, we produce a B that is indexed. That's what this is called when we put our term inside the B to produce a family, to index a B, to get a B of A. So what does this mean? It's a richer system, and we're trying to find a way to reason completely about our program in some mathematical language. And so the question is, is it a rich enough system? Does it provide all the tools that we need? And it turns out that it actually, yes, it does. This is a quote from a paper called Why Dependent Types Matter. And what it ultimately says is that we can specify an entire program, the complete specification of the program's behavior. We can capture that in the dependent type theory. And so what we have arrived at now is effectively a very meandering recapitulation of something that is called the Curry-Howard Correspondence. The Curry-Howard Correspondence simply states that between two formal systems, there exists some correspondence. So this mathematical correspondence to the way that we think about our program is an instance of the Curry-Howard Correspondence. There is the same correspondence between type theory and category theory, or logic and type theory. All of this are related in some way. And so what does this mean for the problem at hand? Well, it really just means that we have a technical term for this thing that has caused me such stress over the last few months. But given that, we know that we can reason entirely about our program from a dependent type theory, but does it help us beyond just giving us a technical word for what this gap is called? And it turns out that, yes, because we can specify the entire sort of behavior of our program in the types, that we can, in fact, make assertions about the correctness of that code. And this is because in a dependent type theory, the terms and the types, this gap between them, is blurred. They both exist on sort of the same namespace, so to speak. And so we can reduce all of the reasoning that we want to make about a program to type checking. A sufficiently sophisticated dependent type checker can actually verify, and we would produce a program which is correct by construction. So given that, why don't we just write our program in a language that is actually executable that has dependent types? This doesn't just bridge the gap, it erases it altogether because the program and the proof exist in the same sort of formal system. But for the same reasons as before, we can't run either of those languages here. Lazily evaluated, non-deterministic memory management, et cetera, et cetera. So enter Rust. Rust provides us, in its type system, a sort of foundational or primitive subset that we can use to start to wedge dependent type behavior into our programs. And I can give you some examples. What we're looking at here is a type level definition of the natural numbers. On the right, we have the dependent type semantics of that natural number definition. And on the left, we have the Rust code. So we would begin by defining the natural numbers as a type, and then we have two constructors. We have a constructor 0, which represents the number 0, and then we have a successor function. And to produce the natural numbers, we just reapply the successor function over and over again. This is called the inductive definition of the naturals. You may also see it as the piano numbers. Now, on the left, we can reproduce this sort of semantics in Rust's type system by gluing together two structs with a trait. And that trait is that sort of higher order thing that lets us treat types like terms. So we can begin to induce our natural numbers at the type level. Now, from there, we can build up. And this example here that we're looking at is a vector whose type is dependent on its size. This is, when someone says, am I doing dependent types? This is the example that we always see. It's kind of the canonical introductory level example. What we see on the right is our vector, which is parameterized. This is a non-dependent type by some type x, which is to say that all of the elements in this vector will have type x. But it's indexed, and that index is how we introduce our dependency by a natural number. And then we have two constructors, the same as before. One that produces us an empty vector, which has type size 0. And then the cons constructor, which is a dependent function that is dependent on that n, the little n. And it sticks things into the vector by taking some x and an existing vector and stuffing it in, and then returning a new vector whose size has been increased by 1, which we get by applying the successor function once. And we have the same sort of semantic objects on the left side in Rust code, where we have our natural number types, and then we have a vector that's holding a Rust vector inside, but it's also indexed by some natural number. And when we do operations on this thing, where we call the cons function, it actually produces a new vector who has a new type that is dependent on its size. So our third, and this example is the most salient for us in particular, because these programs that we're writing here, these very small ad hoc programs, can tend to be fully represented kind of all the way down, to borrow a turn of phrase, in state machines. And not just the individual the programs themselves, but also the communication protocols between the AI and the systems that are responsible for actuation. And we can represent a state machine in Rust type system in the same way that we can give a dependently typed semantics for a state machine. And this one is a little bit more complicated. We begin by creating states that is a sum type, which means it can be either an open S or a closed S. And then we have a type family, which is this ADJ, that stands for adjacency in this case. And the types that are members of this adjacency type family are the adjacencies to each of our states. And so we see on the left-hand side the same objects being kind of recapitulated in Rust, where when we apply our transition function, Rust compiler can actually help us certify that we haven't contravened the edges in this state machine. And we have what you could say is a correct by construction implementation of the state machine. So it does appear that we can map our dependent type theory, or the semantics of our programs, into a dependent type theory from Rust. But as I said before, Rust doesn't actually have dependent types. We're kind of wedging them in through an abuse of the tools that it provides us. And this is not a thing that we can certify. We don't trust Rust compiler to produce correct dependent types. So instead of using denotational semantics to map our Rust program into something in our head because we know that that's how dependent types work, or on paper somewhere and in a LaTeX document, we should instead use one of those languages that we were looking at before that we can actually use a sophisticated type checker to verify the semantics that we've extracted from the program. So we can use this denotational semantics idea that we've used to think about our programs mathematically to map the semantics of our Rust program into some Agda program that can be type checked and certified by the Agda's compiler, who we do actually trust, because it does actually have dependent types. And this begins to assuage my anxiety. I feel a little bit better when I get to this point. But at this point, I have kind of left it at it being purely observational. The dependent type sort of semantics are all in my head thus far. I've said this is what it looks like. I have maybe some rigor applied to that semantic function that maps from one domain to the other. But it's not mechanized. I'd like to be able to include this in like a CI/CD pipeline or something before my program makes it anywhere. So the next step, and this is the step that really helps me feel a little bit better, kind of level off that anxiety into a more homeostasis level, my normal level of anxiety, is the idea of being able to mechanize that semantic function and extract the semantics from our Rust code. And it's at this point, we have built a bridge, I believe, from the program to its proof. And this is still the work that we're actively working on this. It's not a totally solved problem, but what we are doing is trying to figure out what those objects are. What is it, how can we fundamentally represent and then use those as building blocks as we build up the denotational semantics of our program. And simultaneously, I continue to feel better the further we get. So yeah, I think that's it. I'm finished. Thank you guys. I'm looking at the questions if there are any now. I don't see any. In Union Grandee, no questions? Does anybody have any questions?
What specifically is it that it's preventing you from extracting and proof for C++?
It was a couple of things. We would have to teach the extractor individually, like our constraints for the system. Like if it has real-time constraints or it runs on a microkernel, it doesn't have a full POSIX environment. But the second problem, actually, and the code sample that I pulled that from, is using a development implementation of something called libgc. Because in Coq, it is, I think, if not impossible, very difficult to manage memory. And so at the top of that file that I showed, it actually says, you can run it this way and link against libgc, and it'll manage the memory. Otherwise, it just leaks memory, and it'll just eat all the memory on the system. So that is the problem right now, is the idea of thinking about freeing and malloking in Coq is not really a thing, or any of the proof assistance is not something that someone has fully taken on yet. Yes, in the back there.
Is the proof written in Agda or in Rust?
The proof is in Agda. Through the dependent types, we believe that we can specify enough of the program that if it builds, then we can trust it. Now, Agda does have the notion of proofs, and somebody's working on a tactics system as well. And this is a thing that we could, if we wanted to take a step further and go through the process of proving things foundationally in Agda, we could once we have the sort of specification of the program in its domain. Yes, back there.
Have you proved yet the extraction from Rust to Agda?
That is a really good question, and I forgot to say that. This process, we can dog food into the same tool. If we write the tool in Rust, we can have it verify the process as well. Yeah. Yes?
How do you deal with, I mean, in C and C++, it's certainly a problem. In Rust, it can be a problem if you use unsafe code. How do you deal with side effects?
Oh, totally. So one of the ways that is used to model the semantics of a program is something called operational semantics. And it is totally focused on input and output. So there's the example that you see oftentimes is that if you were to think about a program operationally, if you had two programs that you were trying to prove were operationally equivalent that read in a string and capitalized the string and spit it out. If one program did exactly that, and another program did that, but then also deleted your file system, those two programs would be operationally equivalent. And so operational semantics can't capture the side effects, but denotational semantics can, because we're reasoning totally about all of the objects that we're using.
Gotcha.
Yes?
First of all, fantastic talk.
Oh, thank you.
Yeah, second of all, I'm curious because if I understand correctly, most people event spaces are finite types and consciousness. I'm curious why you decided to go with finite types.
Hold on. I think because my predilection is in type theory and kind of functional programming and all that type of thing. And so it was my natural way to kind of approach the problem. And so when I started, the first thing that we did to find out that this was even sound was the state machines. And I had written it in Haskell first, like type level state machines in Haskell, and I just translated it to Rust. And so instead of taking a different approach, it was just because that's where I was standing at the moment that the idea kind of came to us. Yeah. Yeah.
Is there anything in Rust that's been difficult to work around or anything you wish it had that was easier?
Oh, yes, definitely. Writing these programs with this ridiculous type constraint is really hard. It's really not very much fun at all. There is some kind of, like applying some of the ways that we can generalize things in a language like Haskell has made it a little bit easier. Like the state machines thing, we can stick into a monad and then like transition through them that way, so you're not responsible for rewriting all of the functions. But other than that, there isn't yet a solution to that problem. Rust has a nice microsystem that helps a little bit. But yeah, it's just really syntactically heavy. You're writing huge like type bounds for each function. Yeah.
As it's on that, why did you try to go from Agda to Rust?
I think it was, that's actually a really good question. I think because I am not a mathematician, I'm a programmer, and I like to be able to write a program first and then try and derive a mathematical meaning from it, as opposed to reason about a thing mathematically first and then come into the program. Because it's more natural for me to write a program than it is a proof. Yeah.
You may have addressed this, I'm sorry if I missed it, but you talked about proof carrying code and these things, the extractions, tend to carry these giant exponentially sized proofs around with them. Is that, have you addressed that?
Yeah, that is actually not dissimilar from his question before. No, it's fine, it's fine. It's just that the Rust code becomes very long because we're building up these kind of type bounds as the program progresses. Oh, at runtime, no. In Rust in particular, and for us especially since we're not using these pieces of Rust, it monomorphizes everything. So all of that abstraction is erased at runtime. Yeah, back there.
So you have an interesting route. You go from Rust to Agda and then do verification that way. But like you said, there's garbage collection and all sorts of other stuff. You sort of have to trust that your proof checker is doing properly and all those things, right? Like the kernel is, you have to trust it. But then there's also things like ATS, where you start with ML and like a variant of C, and it has pointers, it has free, it has malloc, but it also has dependent types built in. So you actually are building up a C program with verification built in all the way through that compiles to.
Interesting. That I'm not familiar with ATS. I think the situation there would be having to teach the ATS compiler about the constraints that our systems have, like that they don't have a POSIX environment, or it has a real-time constraint or something like that, which may be trivial. I don't know. I'm not familiar with it. But I think the reason why we don't do the extraction process seems kind of related to that, but maybe I'm wrong.
Okay. Thanks.
Yeah. Yeah.
Do you expect to take what you're working on and like abstract it away for other teams that are using Rust that want to also prove?
Yeah, totally. We have tried that as well. And easily the longest professional argument of my life was trying to say that this is a thing that will work. The state machines one in particular, you're kind of beholden to the program counter because the types are being carried all the way through at compile time. And the way that most people want to write a state machine is through a dispatch function and a bunch of handlers. And that is not an easy thing to do in this particular kind of representation. So that is one of the cases where we found to be hard, kind of like the question that y'all asked. Yes, sir.
Was there a reason to pick Agda over Idris?
For me personally, because it was syntactically comfortable, I think. I had already played with it a little bit coming out of my interests in type theory and Haskell. I mean, I think Igda would be, Igda, nice. Idris would be equally as applicable. It was just kind of my preference. Yeah, back there.
Perhaps I missed this in the talk, but can you give an example of where one of your types depends on the value of the actual value as opposed to something like a type called add or something like that?
Yeah, the creation of the adjacency list, each inhabitant of a fully applied adjacency list is a type which is a valid transition for the type that's indexing that adjacency list. So instead of doing a type level add, we have to actually produce a new type from the family of adjacency lists to get our adjacent types in the state machine. Yeah.
You mentioned that you consider the integrative systems to be ASIL 5. Will you at some point apply for certification of some sort against that standard?
Yes.
Yeah,
absolutely. So the standards body that gives us ASIL A through D gives us, has to go through a certification process, and it has a big like development process that has to be certified as well, not just the code. In lots of cases, they don't want to look at a terminal. They want to see everything kind of represented in a formal way. And that is a thing that we have talked about, and we'll have to use a certifier who is comfortable with our kind of weird predilections. Yeah. Yeah, back there.
So I hope I didn't misunderstand one of your last slides. You showed doing extraction from Rust to Agda. What does it actually look like? What does the resulting Agda look like?
We are just, rather than pulling the entire program, we want to pull the specification, which to try and map the types that we're trying to kind of imbue with dependent semantics into types in Agda that represent those semantics. So it really is just insofar as the types and not the like actual execution of the program, at least at this point.
Right, so that's what you're working on. It's not necessarily something you show at the moment.
Yeah, totally, yeah. Yeah.
Is your tool for going from Rust to Agda available?
It is not, no, not right now, yeah. I don't know if it will be. That's not my decision, I guess. Yeah. Sure.
This is unrelated to your topic, but I did want to ask because it came up in my mind as you were talking about it. The thing about successor numbers, is that church numerals? I've heard the term church numerals before, and I was trying to figure out if that's what you're...
It's related, I think, yeah. I think the church numerals are the idea that you can use a function to produce numbers in the same way that I think it may be a more general way of looking at that inductive definition of the naturals.
Thank you.
Yeah, no problem. Yeah.
Have you run into any examples that would pass Rust's type checker, but then would fail the type checker?
No, not yet. No, I think part of it is that we have more handheld Rust compiler than we have Agdas, if that makes sense. Trying to produce an executable program first, and then figuring out how we can map that into the domain of Agda. So that is the hard part, is translating it more so than, I don't know if that helps at all. Yeah. Yeah.
We worked on extraction stuff for a really long time.
Mm-hmm.
Another pitfall of extraction at the time was that you had to execute extracted programs on, if you started to monomorphize stuff and remove non-computational types, values, they were just proofs. You have to run them on a lazy evaluator, otherwise there would be guards that would be missing, and they might go off and execute some path and blow up.
Yeah.
So I don't know, since you're going in the direction, like you just said, you're starting with the program and going back.
Yeah.
You probably don't really encounter that problem, but.
Yeah. Yeah, we.
Is that a thing for you? Is that a thing in the industry?
It's not a thing that I have encountered, no, and we're not running the Agda program, we're just type checking it at this point. So it has been, that's not a thing that I've seen. It's really interesting. It totally makes sense. That would explain why all of the languages are extracted into, that Coq extracts into a bunch of lazy languages. Anything else? We have 5 minutes. Yeah?
So you mentioned that you use the extraction in your CI.
Mm-hmm.
What's the typical workflow, and how long does it take to feedback around?
Still trying to figure that out, but right now we build the Rust program first, And then the extraction program looks at the syntax of the Rust program and tries to stick it in Agda. And we can like catch a compile failure, but it is not a thing that is fully automated that we're like producing objects continuously yet. Because we're still trying to figure out how to use it, to be honest. Anything else? Cool. I guess I'm done. Thank y'all.